Okay, welcome back, everybody. And we're talking about part two of this new partitioning-based CAD flow from Andrew Kahn's group. And let's see, where was I? So let's maybe recap where we were. Okay, so we talked about the original paper that myself and Ehsan and Javid wrote some years ago, and how it showed that if you had more than about 25% of the wires crossing between that you normally have in the routing channels going between interposers, it worked pretty well. But you wanted to have a guide the packer at least with a partitioner, and some of that's probably related to the packer at that time being pretty aggressive in grouping things together, even if they weren't strongly connected. We also modified the placement engine to try to minimize the amount of signals crossing those cut lines, and we modified the router look ahead to understand that there were partitioning lines. So Andrew Kahn's group has built on that by basically using their latest and greatest partitioner. And let's see, what did they do? So they built into that same CAD flow, and they again use the partitioner to guide the packer. And they now take in the molecules that the pre-packer creates, like carry chains and LUTs plus flip-flops, and make sure they don't cut those. And then they constrain the packer, they constrain the placer. And let's see, we go through and we started talking about their partitioning engine, which is pretty interesting. I think that's where we were, right? Was I talking about the partitioner at that point when we finished last week?
I recall talking about the partitioning engine.
Okay, so I'm going to switch over then to the other paper, which is the partitioning engine, which also is their work that they're relying on. And I've made a few enhancements too in this paper. I'm going to make this floating meeting control. Okay, let me make that go away. So their partitioner is a hypergraph partitioner, and it has heterogeneous balance constraints, meaning I could have one for RAM, one for logic, one for whatever I want. And they have a bunch, so that's what this is saying. They call it a multi-dimensional balance constraint. It just means every partition must be balanced within some factor epsilon in all of the resources. So they divide it into, let's see, Jth coordinates. They divide the J coordinate types, and they say you have to be balanced across all J of those. I'm just basically pulling out what are interesting things in them. Okay, so they support fixed vertices, so you have to be in the left partition or the right partition, so they just pre-lock you down. So that is helpful in this work for they can handle locked blocks, something that's locked to one die or another. They have these grouping constraints, which basically is how they're going to handle molecules. So the grouping constraint says these things have to be partitioned as a unit, right? So that maybe these 4 nodes correspond to 4 elements of the carry chain. They have to be kept together, so they could do that. As I said, they have this multi-dimensional balance constraint. It's a hypergraph partitioner rather than a graph partitioner, so they can directly encode a netlist. I can't remember how much I talked about this. I think I talked about the embedding constraint. Do you guys remember that or not? Or do you want me to say it again? It's a week, so I can't remember. This is kind of interesting. So the embedding constraint is a hint of basically I have a vector for every single node. Okay, so some arbitrary dimensional vector, and that gives me a point in vector space for every node, like every primitive in our case. And part of their partitioning cost function considers how close are node 1 and node 2 in this vector space, like what's their Euclidean distance, and that's considered in terms of should they be in the same partition or a different partition. So that embedding constraint could, for example, come from an analytic placement. They're not using an analytic placement, but this is it has some relation to what Alex and Amir are each doing, right? Where they're using analytic placement to guide a clusterer or to guide because you're not using it to guide a partitioner, but using it to guide Alex is using it to guide a clusterer. Yusan is using it to guide a clusterer as well. So they can do this, but it doesn't have to be 2-dimensional. They don't describe it in detail in this paper. They refer back to another work called Spec Part, which I believe is also theirs. These are called spectral methods when you have these graph embeddings for various nodes and use that to help guide a partitioner, or spectral partitioners actually, they just use that, right? Like they'll use that vector embedding and try to find clumps in vector space and say those are your partitions. So they don't go that far, but what they do is they basically get these embeddings, and the way they can get them is by taking the connectivity matrix of the hypergraph, finding its eigenvectors, and you can find, say, the first 20 eigenvectors. And then you consider for every entry, like the 20th entry in each one of those eigenvectors is basically like what is your location in a 20th dimensional space. Say the 20th location in every one of those eigenvectors, for example, would be where is the 20th block in this vector space. Maybe I got the first 15 eigenvectors. I can now go get basically what is your 15-dimensional location. And I can do that for every single block in the net list. Okay, because every eigenvector is basically the same number of rows as nodes that I have, right? Because I'm getting the eigenvectors of my connectivity matrix. So this is a way to basically get what appears to be like a natural location for every block in some high dimensional space, and they can use that, the distance between blocks in that high dimensional space, as a hint to their partitioner. Does that make sense? And I think that's a pretty interesting, it's pretty interesting because we can see an obvious analog with using analytic placement to drive a partitioner or a packer. The other reason I find that interesting is that they have a brief mention near the end of this paper that you could use other embeddings and that you drive through other means. And I think that's pretty interesting for some of the packing work that we might do in the future, like with some of the things that Haidar is considering, where we could use things like GNNs to produce an embedding for every node and say, we don't exactly know what this embedding means. It basically is a vector for every single node, but maybe we can use it as a hint to packing of what nodes that have similar vectors may make sense to cluster together. Okay, so anyway, that was a long thing about the embedding constraint. It's not the most important part of their algorithm. I do find it's a useful tiebreaker, but it doesn't help them that much. But I just find it's interesting because it's a way you could hook a lot of algorithms in. Okay, I think we talked about the timing constraint. And their timing constraint is basically they add up a weighted cut. So whenever you cut an edge or a hyper edge between partitions, there's a cost, and they can have a weighting, which is a function essentially of the timing slack that's expected for that connection. So in this original partitioning paper, they connect up to OpenSTA in order to do a timing analysis of the circuit. It's not very clear what delay model they use. They say they just use a delay model that's inside there, so it's not clear that it's probably not very accurate, but it gives them some notion of timing slack, which they turn into criticality in a way that's similar to the way VPR does it, and they use that to weight the edges that they cut. Okay, so that is part of their timing formulation. The other part of the timing formulation is they also extract some critical paths. So that's what this set P and P is. They've extracted some, I don't know, maybe 1,000, maybe 10,000 paths from the timing analyzer. And they will basically cost it whenever one of those paths is cut. And this I remember talking about this last week. They have this snaking factor, which is basically how many times do you come back into the same partition. And I think that's just because of the way they define the cutting of a path, that they kind of define it as a 0-1 thing of did I cut the path or not? And you'd really like to know how many times I cut the path. And that's where the snaking factor comes in. Yeah, does that make sense? I was thinking about this a little bit of like, what does this path give me that I don't get from just weighting the edges by their timing criticality? And I think what it gives me is if I don't update timing, like I just do a timing analysis before I start partitioning, this is going to allow me to check how many times have I cut this path. Whereas, and therefore maybe it's becoming critical. It didn't look too critical before, but it's getting worse and worse because I've cut it multiple times. Um, Whereas this edge by edge will never see that, right? You'll just see this looked a little bit critical, but not too bad. You cut it. It turns out you cut every single path, edge on that path is a problem. So I think, but this isn't in the paper, there's kind of an interplay of how useful is this path term. I believe will interact with how often do I retiming analyze? Because another technique for optimizing timing is just as more information becomes available, like I've done some partitioning, so I actually know a better delay model and I can see where how critical every edge is now. If I update that data more frequently as partitioning proceeds, it can make this less important or possibly not useful, right? Because I'm already getting directly incorporated into my edge weightings in new information about timing. Does that make sense? Because whenever I see like a direct path monitoring, I kind of want to know why did I have to monitor the entire path? Why couldn't I just monitor, the edges that compose it? And the general reason is, well, I might want to see, am I doing bad things to the whole path, right?
So
Which
Vaughn, just to
doesn't
confirm,
directly fall out of this formulation, which is why it makes me think that an alternative would be to drop this term and just try to retiming analyze more often as partitioning proceeds.
Javon, just wanted to confirm. So the left one's only on a per edge basis, the right one's on a per path basis.
Yeah.
Gotcha.
Um, okay, so that's how they do this. And let's see. So the partitioner itself it's quite a sophisticated partitioner. So there's many components to it. I think I'm gonna try to give you a flavor for a bunch of it, but if you want every detail, you have to ask me lots of questions or read the paper and read the paper probably in detail. Okay. Um, okay, so what do? This figure kind of shows it all. It's like a multi-stage algorithm. So one thing that you'll find in partitioning papers is, you know how placement has seed noise? We run the seeds multiple times because we get better or worse solutions. Partitioners appear to have that, but more. Okay. Because partitioning papers usually will do a lot of multi-start. They'll say, I took the best of 50 trials and so on, which is a sign that they get a significant variation in the quality of solution depending on what their starting point was. So they acknowledge that essentially by saying the first block here is let's try different orders of vertices. We're just going to try the same algorithm, reordering the vertices a bunch of times, and we're going to see which one gets the best answer. The next, and that also allows them to get some parallelism, by the way, too. So you can see they show like a bunch of these blue blocks, and it's because they can run these in parallels. So just invoke the same algorithm with different vertex orderings, and then we're going to pick whichever one or ones look best. Okay, so what do they do? Okay, so how does this actually work? They first coarsen their hypergraph, and there's a bunch of discussion about each one of these steps. So let's talk about, um, let's see if I can find like where they talk about coarsening it. So there's a section on each one of these things. Okay, so here's the coarsening. Okay, so they got a bunch of vertex orders, got a bunch of partitionings proceeding in parallel. First thing each one of those does is it does this coarsening step. So they want to basically reduce the size of the hypergraph. So they're going to find nodes that they're going to group together, okay? And they're going to be kept together throughout this partitioning. The technique they use is first choice clustering. And basically they have a function here, which is what is the weight of an edge divided by its fan out basically fan out. Okay, so what's the weight of the edge divided by fan out? And then they basically take two nodes and they say, well, let's add that up for all the edges that go, hyper edges that go between them. Okay, so I've got a block, it connects 3 times this other block, and some of them are timing critical maybe, so they have high weights and they're low fan out. That's going to have like essentially a high attraction. They call it like the heavy edge rating function, but this is basically very similar to some of the attraction functions in TV pack or AA pack, sorry, or AP pack. What's interesting in their algorithm is they don't actually try to go find, for example, what is the best edge, like what's the best pair of vertices to group together. They just walk through the vertices in the order that they've chosen. So this is why vertex ordering matters a lot. And they basically just pick vertices to merge. And I had to go back and like look at the details of this, but I think it's basically you hit a vertex and you just pick who do you want to merge with, right? So it's like a greedy algorithm. And you go on to the next vertex, who do you want to merge with? So, and you can see how that's immediately greedy. It didn't go through the whole list, seeing who has the highest merge coefficient with anybody else. They're just like, who's first on the list? Who's your merge? Who's next on the list? Who's your merge? Does that make sense? So that makes them pretty dependent on node ordering, which is why they try a bunch of different node orderings. So this is a very fast coarsening algorithm. And yeah, gives them like a smaller hypergraph basically after they've applied it. As they're doing this coarsening, they maintain groups of molecules basically, what we would call molecules, the things that are pre-packed, they'll be kept together. And they don't just use that heavy edge function, they also bring in they basically take the edge attraction function and they add in something that's inversely proportional to the distance between these two nodes in the embedding they have. And their embedding was, again, this like embedding into a k-dimensional space. But for us, it might be an analytic placement. Let's see.
Sorry, Vaughn, just a quick question. They call it
Yeah.
embedding constraint. So are they constraining something to be true, or is it more of an objective?
It's an objective.
Gotcha. I just wanted to
Yeah.
confirm.
Yeah, you're right. The constraint is not a great word here because nothing in here says that it's a constraint. It's basically an embedding, like a guidance. It's like another form of attraction.
Yeah, I know I'm just splitting hairs at words here. I just wanted to check. It wasn't like we're guaranteeing a certain distance. We're just saying we're trying to minimize that distance.
No, yeah. And it's a weighted function. So it's basically this is that, add up the weights of all the edges between them. And this is also add in another term with some weighting rho, which is proportional to the inverse of the Euclidean distance between these things and whatever vector space you've embedded them. Does that make sense? Okay. And as they do this merging, because they do it for a while. Okay, so this coarsening can be done for multiple steps, so they can actually keep grouping over and over again. So they'll go through all the vertices saying, who do you want to group with? And then go through it again and say, okay, now for the merged vertices, who do they want to group with? And they keep making that less smaller and smaller. As they're doing that, they have to keep track of, well, for the merged vertices, where would they be in the embedding space? So they basically take a weighted average of where the components were, okay? And the weighting is basically each of these things has, in our context, it would be kind of like let's see, it's not clear that we would have different weightings, but they can have nodes that have different sizes essentially, right? So they compute the new embedding of the merged block as just the weighted average of where were all the components in vector space. And it's a weighted average because they assume they could have like essentially different masses using like Alex's notation. And their masses are vector masses, right? They don't call it that, but the fact that they have these heterogeneous balance constraints means essentially they've got a vector of what are you, right? You're a little bit of LUT, you're a little bit of RAM, for example. Let's see. This one, I think I have to actually go back. This is pretty weird. And they talk about it later. So they have something called community guidance and cut overlay partitioning that I'll try to explain a little bit later. Okay, so does that make sense? So they shrink down the size of the hypergraph. Then they produce an initial partitioning. So they they've got a whole bunch of hypergraphs now, and the most coarsened one is HC. So they basically have, H0 is not coarsened at all. H1 has been coarsened where people have been paired up. H2 pairs have been paired up and so on, right? And HC is like highly paired up, okay? And because HC is relatively small, because they've done several levels of this coarsening, they say they can use things like integer linear programming becomes a feasible technique to actually find a partition because it doesn't have that many nodes. And they basically throw the kitchen sink at the partitioning. So they basically, one way they make initial partitions is they'll do random ones. So they're just like, they're down to 50 or 100 nodes, and they just divide them randomly into two partitions. But they'll do that. They'll do a bunch of different trials of that. So they'll try a bunch of random initial partitionings. This vile one is like, it stands for very illegal initial partitioning. I think it's like highly unbalanced. They try to put most stuff in one side or the other as another starting point. And they can run ILP. Okay, so they've got it down to 50 or fewer nodes. They actually can run ILP on it to get like the optimal answer for the initial partition. Does that make sense?
Well, what is ILP?
ILP stands for integer linear program, and this is their integer linear program description. Okay, so integer linear programming is it's kind of a powerful technique that people use where if you can encode all your decisions into integers. So in this case, for example, they make a variable x v I, okay, for each I in one case. Okay, so I in this case is the partition number because they can actually partition into more than two things. So they can be partitioning into k different things. And this first integer variable they defined is basically, am I in partition? Let's see. I have to be in some partition. Okay. So V is, I believe, for each block V, we introduce these variables for each vertex. Okay. So X, this is a variable that exists for every single vertex. They use this notation of block is basically partition. So they're saying there are, let's see, okay, let me see if I can figure this out. I did actually figure this out when I read the paper. Okay.
Things like the coarsened, the clusters, I guess they got after coarsening.
Yeah, that's what they're doing. So they are basically deciding what partition, this is basically what partition are you in, okay? XV is one for every V in V.
From what I understand it, at least for that first line, I think it's just saying that every block is placed in one and only one partition. You can't be placed in two because then that would add up to two and it's not equal to one.
Yeah, no, that is what it's saying. I'm just trying to remember like what all their notation is so I get all the variables right. So let's see what if they are doing, I think, a k-way partitioning. So let's see. They have lots of different dimensions here. So I just try to make sure I remember 1 upon k. Yeah, okay. So k is the number of partitions. Okay. And so I is which partition are you in. So there's a variable for every single partition, and it's a variable for every single block, which I guess is like the course and net list. Yeah, so I think that matches what you just said, Alex. They, in one of their other papers, they kind of redefine what block means, which is part of what was screwing me up here. Okay, so I didn't really answer your question, but basically, if you can actually phrase a problem as a bunch of integer decision variables. So this first line is saying, I will have a bunch of constraints that if I add up all these decision variables that basically say for a certain block, like block 20, are you in partition 3 or not? So that would be x of 20 comma 3. So some variable, I just given it that name. It's 1 if you are in that partition and 0 otherwise. Okay, so this first, and now you have to, so that encodes your solution, right? Those x variables will actually tell me my answer, but now I have to have constraints. So this constraint that the sum over all partitions from 1 to k for every one of those blocks, v, it has to add up to 1 is exactly what Alex just said. You must be in one partition, okay? And it also has to be integers. So you did 0 or 1. And this will therefore put everybody in some partition. They define another variable here, which basically is for every hyperedge, is it completely contained in a partition or not? Okay, and they define that as essentially, if you think about this carefully, this constraint that this y variable, which is saying is an edge captured inside of a partition, must be less than the x variable for all of the things it connects to. That actually implies the capture of an edge only occurs when all the things it's connected to are in that partition. And then that edge is captured in that partition. They've got, yeah, and then this one I think is the balance constraint. No, because this one is the balance constraint. So these formulations you tend to have to go through really carefully. I did when I read the paper, but I now got the first two, and the other ones aren't quite as important. So I'm not going to go through them because I'll screw myself up. But if you can code your problem this way, there are solvers that are basically pretty good at exploring the space. They have to go try a whole bunch of different integer assignments to try to find the best one. And to find the best one, you have to define some objective function. And this is their objective function. So their objective function is basically maximize the capture of weighted edges. They already have these weightings for like timing and so on, and they say, let's try to capture as many edges as we can when they're weighted by this function. And there are ILP solvers that basically will go explore the solution space for you now efficiently. They run out of gas when the problem gets too big, because this problem is, the actual complexity is exponential. Like the brute force way to do this is you try all the possibilities. These solvers are pretty good at basically figuring out all the possibilities that have, blocks 2 and 3 put in partition 4 are bad, and they will stop exploring them. So they in practice work better. They control the exponential growth better than if you just wrote some naive code, but they eventually run out of gas if you give them a big enough problem. So that's why it was important they got this down to like 50 coarsened blocks, and then they can run something like ILP. Does that make sense? But the nice thing is they've also had to simplify their objective function a bit. Like you'll notice this doesn't have the path constraints and so on. So they simplified the objective. They had to have a smaller number of things, but now it gets under those constraints, it gets the perfect answer. And most other algorithms don't guarantee that. They can get stuck. Does that make sense?
Yeah. So is it just kind of like some sort of minimization problem with like integers, essentially?
Yeah. It is a minimization problem. They have defined this function, and they're not minimizing in this case, they're maximizing, but they're maximizing it. And all the solutions that they can evaluate and consider legal must meet these constraints. Okay. The first one is the important one, right? The second one pretty much just defines what does edge capture mean, because they want to use that in their objective function. Does that make sense?
Yeah.
Yeah, if you take a very good convex optimization course, you'll learn a lot more about this. But yeah, there also need to be linear, which is why you don't see any square terms or anything like that. It's always linear.
Okay, so that whole thing was just to get an initial solution. Okay, they got a whole bunch of vertex orders. They do this coarsening. They do some random partitions. They try that a bunch of ways. They make some highly illegal ones. They make an ILP one, and they got a bunch of initial partitions now. Then they go off and they refine those initial partitions. And again, they're not doing just two-way partitioning. It's K-way. So they might be partitioning into 4 things or 8 things or whatever. Okay. I'm pretty sure you would not know this, Samuel, because there's no way they squeeze this into the second-year engineering science curriculum. Insane though they are about throwing material at you. How many people here know what fiduciary math partitioning is? FM partitioning.
0 for me.
Okay, nobody. Okay.
I have my hand
guys
up
think you might?
on, and also Sahel knows this.
Yeah, it's a CAD course. Yeah. So it's a classic partitioning algorithm. It's an iterative partitioning algorithm. So what it does, it needs to have a starting point. So it takes these initial partitions, and then it basically tries to move things between them. So it's an iterative exchange algorithm. The clever thing about it is it can do hill climbing. So it kind of exchanges it looks through all the things in each partition and says, which one of these should I move to the other partition to basically minimize the cut size or maximize my objective, right? Like they have a somewhat more complicated objective than just minimizing cut size, as I showed you. But it basically picks what's the best one to move, and it moves that. But it doesn't stop until it's moved them all, which allows it to do some hill climbing. And after it's moved them all, it goes through and it says, now that I can see every single thing that I did, where should I have stopped? Okay, so it gives it some ability to hill climb. So one of the things they do is they use K-way pairwise FM. So usually, probably when the CAD course, you study 2-way. You can actually generalize that algorithm to say, well, instead of saying, you can say, where should I move? Not just like who's the first thing to move, but also which partition should it move to? Okay, and that's a generalization to K-way partitioning of this FM algorithm. So they apply that. Well, actually, they do 2. What I just described is direct K-way FM, where they generalize the algorithm. These are heuristic algorithms, so that sometimes doesn't work as well as actually just taking, I've got like 4 things, and I'll just basically take all pairs of those, and I'll run FM partitioning between the pairs. So that's what they do by K-way pairwise FM. They just find a bunch of pairs. I don't know if they actually choose. Yeah, so they don't do all K-squared block pairs. They just choose like K/2 block pairs. So they choose what seem like promising ones, and they run FM between all those block pairs. So that's one thing they do. They also run FM, basically a generalization of FM called K-way FM, where as you're moving things, you're deciding where to move them to, and they're all moving around at the same time. So do both those things and take whichever one gets the better answer. And then they also have another refinement algorithm, which is kind of like a multi-move that we do in the VPR placer. So in VPR, sometimes we'll grab, actually, do we do this or not? Let me think about this. Actually, we don't do this. Okay, no. Okay, so in another CAD tool I've worked on that we do. So it also had the name VPR and also starts with Q in its commercial version. This is a multi-move in placement terms. So what they call greedy hyperedge refinement is they find an entire hyperedge, a net that connects maybe 6 blocks, and they say, let's just take all of these blocks and put them in one side. Maybe 3 are here and 3 are there. Let's take the 3 that are in the left partition and put them in the right partition. And the reason for doing this is you can get stuck, right? You're in kind of a deep local minimum where you got 3 blocks on each side, and anything you do doesn't actually help you. But if you could try moving all 3 terminals that are on one side to the other, it helps you. The same thing can happen in placement, where you kind of get stuck. You got half the critical path on the left side of your circuit, you got half on the right side. Moving any one block doesn't seem useful, but if you can find the whole other half of the critical path and say, let's move it all over here, that can be useful. That multi-move is actually a little more complicated than what they're doing. But what they're doing is, finding these hyper edges and trying to collapse them. And it's to get out of local minima. Okay, so that's all. And so they're kind of keeping track of what did best on all these things. They're refining these. They have many initial partitions. They refine them using these different algorithms, and I think. I think they choose the best of these. I think they may also run them somewhat on top of each other sometimes. So I have to read it really carefully to see if they do that. Okay, and then they also do these refinements repeatedly. Okay, so they've coarsened the graph, the hypergraph, so there's not too many terminals. They get an initial partition, they refine it, then they uncoarsen it. So they remember what was grouped together, they ungroup it, they refine it again. They keep ungrouping and ungrouping and ungrouping, and they get down to the bottom level, and they're actually now moving around individual nodes again. This one was really tricky in a way. Okay, so what they call cut overlay partitioning, I don't think I can give you a great explanation because I don't know if I understand it super well. But effectively, what they do is they try to take parts of one partitioning solution and apply it to another partitioning solution. So, so they've got all these candidates. Because they've been, they started with many different initial partitions and so on, they can actually keep many different candidate partitionings alive as they go down and refine them. And they actually go and look for, let's see, they go and find across the solutions that they have and they've kept and they like, hyper edges that they find the hyper edges that are cut in those solutions and they remove them from the graph. And then they find the strongly connected components in what's left. Okay, what that means is they're basically finding nodes. I believe what this is doing is finding nodes that are kept together in the same partition across many different partitioning solutions. Okay, so they're actually extracting essentially commonality from a whole bunch of candidate partitioning solutions that they've created. And then they basically take those things that seem to be consistently kept together and they merge them together. Okay, so they say, I will force these now to be kept together. And then they basically go off and start refining that. So they run that back through some of those refinement algorithms I just talked about, where they've said, one of the things I figured out from these earlier partitionings is that node A, B, and F seem to always be together. I'm just going to squish them together to make sure that's maintained in any future solution. And I'm going to run through my refinement stuff again. Okay. And they call that cut overlay clustering and partitioning. It's pretty complicated, but it's kind of interesting. They're trying to extract commonality from their solutions and then say, let's try to take that out of the problem space and run back through our optimizers. Okay, then the last thing is this V-cycle refinement is a classic partitioning approach. HMetis uses it too. It basically means they've already kind of done it, but I guess they do it again. Basically, it means cluster, 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 and then refine your partitions, refine your partitions, refine your partitions as you uncluster. And they take their solutions and they do that again, right? They say, let's go recluster them and do multi-level, like do refinement at each level, and then let's cluster them up again to get to pretty big clusters. Let's refine those, and then let's go back, let's uncluster and refine. It seems like they already did this. Like this was part of how they kind of created their solutions. So I think they're just kind of running it again because they've got so many different things they're running in sequence. They're like, maybe we'll find something better if we just do it again. And okay, yeah, okay. So that was a lot of information. I'll pause for a minute in case you guys want me to answer anything or discuss anything, or just like, please stop talking about partitioning and go on.
I did have a quick question. They're making a lot of possible partitions. So they make a million, or not a million, but they make a ton of different initial guesses. Then they make, during their coarsening step, they make tons of different placements. And then during the decoarsening, they also make tons. When does it recollapse? And does this hurt runtime at all, or what's going? Like there has to be a catch for.
I think they use parallelism quite a bit. So part of it of making many initial solutions, they'll keep some of them around if they have enough processors. So, and I'd have to go back and read it really carefully to see, but part of it is that they're using multi-candidates to leverage parallelism. Does that answer your question?
It does, but I'm also kind of concerned because netlists can get really large. So memory could also become a problem if you make like yeah, you can keep throwing cores at it. There are 128 core machines nowadays, but then not many of them have like 128 terabytes of memory.
Yeah, partitioning doesn't have that much memory per node. And I also don't want to give you the wrong impression that they keep every candidate around. They
Oh.
have like they go off and they basically they say, okay, let's try a bunch of different vertex ordering so we get different coarsenings, and then we get up to we take those coarsenings and we run them through our ILPs and we run them through FM and all sorts of what our ILPs and our random partitions and so on. They're kind of pruning the solutions. It's not like they're keeping every solution they get at that. They have some heuristics of like, well, how many of those do I want to keep? It might be tied to how many cores they have. But they evaluate which ones look best, and then they'll start uncoarsening and refining those. Does that make sense?
That makes sense.
And then but they have some number of them that get to the final answer, and then they take those and they can run this cut overlay partitioning where they say, okay, maybe I got 40 good solutions now. I'm going to try to extract from them these strongly connected components that imply consistent substructure, squish that substructure out, and effectively rerun parts of my algorithm now with that, seeing, well, does that get better?
Mm.
It's
just very it's just very interesting because like we can probably do something similar in the Packer. I mean, the seeds are very like the ordering could probably be shuffled a little bit, and we can just try and do like 4 parallel threads and just see what 4 get the best clustering.
Yeah. Okay, so this is a little more information on timing. This is their edge weighting for or timing cost of a path. And basically, this is a criticality formulation. They did a timing analysis using OpenSTA. They said they just used its wire load model. So that probably means like OpenSTA doesn't really know what they're doing with partitioning. They just basically this will mean that OpenSTA will use a bigger delay for nets with more fan out and stuff, right? It's going to be a pretty crude delay model, but it will capture this thing has 12 nodes in series on a path and has high fan out on some of the hyper edges and so on. And they're going to get a slack, and they basically normalize that by clock period and then take 1 minus that to some exponent. This is very similar to the criticality computations in VTR, right? So this is like yeah, so it's so that's pretty probably familiar. And yeah, this is basically the same thing for edges. Like so the edge formulate weight of a hyper edge is basically a function of its slack. And I guess this is actually another way they're bringing the paths in. This is like a little bit of path counting because they take all the critical paths that extracted and they'll add a bit more criticality every time they see that a certain edge is part of this path. So that's a little bit of path counting. It's done in a somewhat brute force way. Like you extracted, 10,000 paths and then you counted how many times the following edge occurred on them. But it basically gives them a little more information on their edge weighting. Because it's kind of like what we showed in one of the group meetings, right? If you show up on many, many paths, that makes you a bit more important. So they'll capture a bit of that too. This is just basically how they adjust when they're coarsening. They take into it their attraction function takes into account timing. That's all that is. And we talked a bit about this, I think, the other day about this snake term. And my take on the snake term is it is really just kind of fixing up the fact that their basic term for a path is like, did I cut the path or not? The snake term now brings in how many times did I cut the path? For me, it's a little more natural to just think about how many times did I cut the path right away, but I guess in a partition is the way you formulate it. And then they have something they call timing aware refinement, which basically means they retiming analyze. So they do have a refinement to this where after they get a partitioning, they can update their delay models, go back to the timing analyzer, get updated criticalities, and redo the partitioning. And it's much like what we do in placement, where once in a while we retiming analyze and say, let's update all our timing weights and adapt to that. So they do that in a sort of more coarse way. Okay, so then they have a whole bunch of results. guess to summarize the results, they basically outperform HMetis, which is kind of the classic partitioner, and SpecPart, which just uses that spectral embedding in vector space, um, by a reasonable amount. And this is cut size. And let's see, HMetis is 1. So you can see they are this orange curve. So sometimes they're about the same. Sometimes they're like 15% less, and one of them are like 40% less. Okay. And then if you go to more partitions, this is where it gets confusing. They actually are using the term blocks here to mean partitions. They outperform HMetis by a little more. And there's a bunch more data in here. But basically, the end result is like they are more feature rich than HMetis. They can handle these heterogeneous balance constraints, this grouping of things, etc., and they outperform it on the by some amount, not by huge amounts, but by some amount on the cases that both of them can handle. And let's see, what else is there to say on here? I think the rest, there's just too much data for me to go through, but basically the results are good, is the high level summary. It is a good partitioner.
Were they
They
tested
have
on?
some,
Okay.
this stuff is like how fast should they partition, how fast should they coarsen, I think. They basically, these are parameter sweeps of how did they tune up their own, how did they tune up like how many solutions to keep? You know, to Alex's question of like how many good solutions do you keep at each phase and how fast do you coarsen and so on. I don't think I'm gonna, if you're interested, you can go through and see like how they tuned it all up, but they checked it all.
Was this tested on FPGA or an ASIC? Like when they were
Well,
doing it?
they're not testing on either. They're testing on, they test on the Titan benchmarks actually.
I noticed
That's
that.
one of their main benchmark suites. But they also test on some other ones, REN, which I don't know, but I think that's an ASIC focused one. And then they don't put it on an FPGA or an ASIC, they just evaluate the quality of the partitioning.
You know, what I meant by that was like they had to give a delay model to OpenSTA that was like which was load based. And were they pretending like they were putting this on an FPGA? Or were they pretending, or does it not really matter?
I think the timing ones were all done with the ASIC stuff. That's a good question.
Gotcha. I
Were
was
they
curious
just
about that.
that is a good question. Okay, so these are all cut size. They're on Titan. So I don't see timing results on Titan. So it might be
Ah,
because they're using OpenSTA, so that they didn't quite know how to timing analyze the Titan designs.
that makes sense. Okay, that makes a lot more sense.
And I don't know exactly when they were. Yeah, you'd have to read all the details of this. They're using OpenSTA to extract critical paths, and they're checking how many of those paths are cut. I don't think they really put in a model of what the delay of a partition is. It's more like they found critical paths and they checked how many of them are cut. Does that make sense?
Yep.
Because there's not a lot of physical detail, like how much it matters. Yeah. How likely you are to make new critical paths depends on what's the extra timing cost of a partition. And I don't think they don't evaluate the results that way. They don't really have a model of that. And that would be pretty technology specific. Okay, so that I went through that. Let's pop the stack back to this one. That's a big part of this paper, though. Okay, so this paper where they integrated partitioning into a CAD flow for interposers, a big part of it is using this really good partitioner. And so let's go back to what they did, though. This is just an overview of that partitioner. So it uses multi-level clustering, an initial partition, and multi-level refinement. So I guess if you want like a succinct description of like how does this whole thing work, there's their description of how it works. And you can see within each of them, though, they have like the initial partitioning has these multiple ways they do the initial partitioning. So they're kind of creating multiple options and populations of solutions as they go through this. Let's see. And this is kind of just showing they start with the circuit netlist, so like the Titan designs. They use VPR's pre-packing to create the first grouping. They use these growth algorithms, right? Like the heavy edge matching and so on to gradually cluster, and they get the coarsest graph. Then they create the initial partitioning of that, refine it, and uncourse and uncourse and uncourse and uncourse and refine, refine, refine. So that's the basic algorithm again. And let's see. So this is kind of the details of all that. This part I don't know if I fully understand. I guess I don't fully understand it. I think this is a CPU time improvement. They call it FP growth. It looks like they basically try to find essentially pattern matching. I kind of like to do the following, like group these things. So I'll pattern match so I can group them faster. I confess I do not fully understand exactly why they're doing that. Yeah, so that it's kind of interesting. I don't, but that's another enhancement where I think it's being done for uh speed. Oh, actually, look at this. This is actually a technique that we probably wouldn't do this. This is a technique that they're using to take the timing critical paths that they've extracted, and essentially find regularity in it and store it more efficiently. There's a problem whenever you have a path-based optimizer, paths in a circuit are exponential. Now, if you only extract the critical ones, you try to limit that, but you can very rapidly get like, even if you say I want paths that are moderately critical, you can start getting, I got 100,000, I got 1,000,000. It explodes on you. So that's why in VTR, we tend to use edge-based formulations a lot more. Like you analyze the paths, you turn it into weightings on the edges, which are like the connections, which are not going to explode on you. They are part of their timing formulations you saw has some number of paths that they've extracted. So they actually have a whole thing in here about how they try to extract patterns on that so that they can represent that more efficiently and update it more efficiently. Yeah, and then as you saw in their previous paper, they use ILP to get, that's one of their powerful techniques to get an initial partition when they have coarsened the hypergraph a bunch. They have another technique here where they basically constrain the ILP solution to what they think is the promising part of the solution space, and they call that neighborhood influences. So with other heuristics they come up with, I think these things should be in the left partition, and they'll just constrain that in the ILP solution to make it converge faster. So it's kind of different. Like they have ILP that can search everything. They have the heuristics that don't. They'll take stuff they're pretty confident of from their heuristic solutions and basically constrain the ILP solution to say you must respect this, which means it's no longer guaranteed optimal, but may help it scale, like may help them solve some bigger problems. And presumably because they do this, they find this is a bit better than just running the heuristic itself or only using the ILP when it can handle the problem size. And let's see. Okay, and that's kind of it. So then what did they get? Basically they get routed wire length and frequency on the Koyos benchmarks. And let's see, I have to remember what they achieved here again. So they basically are trying different partitioners. This new one is called FPGA part. Let's see if I can make this bigger. This is like, how much better are they? Okay, so this is a 2-die architecture. This is a 3-die architecture. So we'll just look at the 3-die architecture. FPGA part is green. It gets noticeably better wire length and kind of noise on Fmax, not very clear. Triton part is their earlier paper, and it does a little worse than their enhancements in this paper on wire length, but maybe a little better on critical path. So their main gains are on wire length. They get somewhat better wire length than you would get from Metis or HMetis.
It's an interesting graph to use because everything's continuous.
Yeah, that's actually true. It's interesting that it's not a good idea to actually fit
Yeah.
to that. Yeah, good point.
It just kind of concerns me because it makes it look like what is 0.5 of Bitcoin mining?
Yeah, okay, then they have all sorts of data on here. So they get small improvements. So I guess this gives like what do they get by employing their partitioner? And it's not huge improvements versus using the interposer aware branch of VTR without partitioning. And I guess basically they get improvements of like 5% in wire length, 2% in critical path delay. Which is not overwhelming, but is noticeable. And that's with like 4 dice. They get a little bit less if you have fewer dice. I guess that was with okay, that's the VTR7 designs, which are pretty small. So we use Koios, which is probably a better test. Then their gains are a bit bigger. 10% wire length, 5% F max, which is actually pretty good. So that's a pretty significant gain. And I guess I have to look at what they said default VTR7 is. Okay, and they're comparing it to VTR with no partitioner. Okay, so this is the improvement they get with their partitioner. And yeah. So one of their other results I mentioned, they had this thing they called neighborhood influences, which is they're taking something they've discovered through heuristics. Like I think the solution should have these nodes in the left partition. And they're comparing what cut size do they get on a bunch of Koios benchmarks when they use that versus they don't. And basically, they get about the same cut size, but they get a much reduced CPU time. So say they can make the ILP faster by giving it constraints that they're fairly sure are a good idea, but they can't prove are a good idea. And that's kind of about it. They've got a bunch of detailed results where they run many seeds and so on, right? And see how well does this route. It routes better with the partitioner than without, and so on. Okay, that's it. That I think I've given you guys more than enough detail, and I think I'm over time. Sorry.
Vaughn, a quick question before we end. The point of the original paper, if I remember correctly, was to measure how many wires do you need to cut between the between 2 die, like to be how many wires need to be cut between die. Do they investigate with their partitioner? Does that reduce? Does that increase?
Let's see. It's a good question. That might be.
This page actually.
Yeah, here I think they're looking at a few different evaluations on that. Okay, that's seed noise. I think it's basically okay, routability evaluation. They don't
80,
study it in great detail. They try 80 to 95%, and they find with their partitioner it's better than it was without it. But they don't really try to answer that architecture question. They just want to say, are they helping with it or not? And they are helping with it.
Gotcha. That's actually what I was curious on, so perfect.
But basically on the left side is like what happens if you don't use a partitioner with the VTR7, interposer branch. So you can see like this red design, for example, as they remove more and more wires, it basically stops routing, right? Goes from 100% routable to never succeeds. And with their partitioner, it's pushed out, right? At 90% of the wires removed, they still got a pretty good chance of routing it, whereas here it was maybe 50-50. And they've got some that are routing at maybe 92%, whereas here there's really nothing there. So they have pushed out the frontier of when does it break somewhat. Does that make sense?
No, that makes lots of sense. And the axis starts at 80, and that was the number that was reported from the prior paper, so that makes sense.
Yeah. Anyway, I enjoyed reading these papers. They are dense reads, but they are like kind of a master class in like optimizing like what are things that you can do to make a partitioner really good. And they have analogs to other parts of CAD. Like it is like many, many ideas. Let's combine them together. So yeah, they're dense reads, but they're interesting. Cool. Okay. Thanks, everybody.